So now we are going to embark on a classification of acid and base strengths. And in this lecture, I am going to define strong acids and bases and teach you how to do calculations of pH for strong acids and bases. So first, let's define the strong acids. By definition, a strong acid is a species that completely breaks apart in water. So strong acids completely dissociate into ions in water. So let me just give you the generic case, HA. HA is a fake generic acid. If I put HA into water, I'm going to put water over the arrow, it completely dissociates into protons and the anion. This would be the A minus anion. This is complete dissociation, so I'm not writing this as an equilibrium reaction. I'm writing an arrow going all the way to the right, all the way to completion. This goes 100% to completion. Another way to write this reaction is that the acid HA interacts with water. Okay, so here, instead of putting water above the arrow, I'm including it as a reactant. If I write it that way, then instead of forming just a proton, I write the acid as hydronium, and the anion stays the same. So those are two absolutely synonymous ways of writing down the dissociation reaction for a strong acid. Now, there are relatively few examples of strong acids, and I would like you to memorize the 6 major ones. The 6 major strong acids that I would like you to memorize are the hydrogen halides HCl. So these are the ones that you need to memorize. HCl, HBr, and HI. So these are all of the hydrogen halides except HF. HF, hydrofluoric acid, is a weak acid. But hydrochloric acid, hydrobromic acid, and hydroiodic acids are all strong acids. These 3 completely dissociate in water. The other 3 are H2SO4. This is sulfuric acid. HNO3, nitric acid, and HClO4. This is perchloric acid. So sulfuric acid, nitric acid, and perchloric acid are the ones containing oxoanions that I would like you to memorize. So just to repeat, hydrochloric acid, hydrobromic acid, and hydroiodic acid. Sulfuric acid, nitric acid, and perchloric acid. These are the 6 strong acids that I would like you to memorize. Now, what happens when any of these dissociates in water? Well, we can write an example reaction. Let's just take HCl. HCl plus H2O, if I stick that one in water, it completely, oops, I'm sorry, I put water redundantly. It completely dissociates. Okay, so here I'm using water as a reactant. So what I'm doing is I am forming the hydronium ion, and then the conjugate base would be chloride. So in this reaction, we have complete dissociation, and I have the acid interacting with water, which acts as the base. On the right side, the hydronium would be the conjugate acid that is associated with the base. And the chloride would be the conjugate base that is associated with the acid. Now, what is special about strong acids is that their conjugate bases are weak. The conjugate base chloride cannot compete with the base strength of water. Okay. In fact, the conjugate base chloride is so weak that it actually is a non-base. It's not even a weak base, it's a non-base. The conjugate of a strong acid is a non-base. So basically, there's no strength in it to push the reaction in the backwards direction. So knowing that a strong acid undergoes complete dissociation, we can do calculations. For example, calculate the pH of a 1 times 10 to the minus 3 molar solution of hydrochloric acid. Now, you know that hydrochloric acid undergoes complete dissociation. We just wrote the reaction for it above, right? So because dissociation is total, okay, so since dissociation is total all the way to completion, 100%, the hydronium concentration in that solution is going to be equal to the original concentration of HCl, whatever it is. So that means that once this reaction has gone to completion, I'm actually going to get 1 times 10 to the minus 3 molar hydronium, or protons in solution. So the pH is going to be the negative log of that. Of course, pH is the negative log of the H3O plus concentration. So that is going to give me a pH value of 3. So a 1 times 10 to the minus 3 molar solution of HCl is going to have a pH of 3. If it's more concentrated, for example, a 1 times 10 to the minus 1 molar solution of HCl would have a pH of 1. A 1 molar solution of HCl would have a pH of 0. Okay, so the more concentrated the HCl is, the lower the pH is going to be. And it's very easy to calculate because dissociation is total. Now let's talk about strong bases. Like strong acids, strong bases are defined as species that completely dissociate in water. So these completely dissociate in water. They tend to be metal hydroxides. They're not all metal hydroxides, but I'm going to put M as the generic metal with a hydroxide. Metal hydroxides tend to be solids, and when we put them in water, they undergo complete dissociation. So here, this would be dissociating to the metal cation and the hydroxide anion. So this is 100% dissociation. This is not an equilibrium reaction. It goes all the way to completion, complete dissociation into ions. That's what defines a strong base. So strong bases, for our purposes, you can think of the strong bases as all group 1 and 2, that's the alkali and the alkaline earth metals, all group 1 and 2 metal hydroxides, hydrides, and oxides. So hydroxide is the OH minus anion, hydrides would be the H minus anion, and oxides would be the O2 minus anion. So whenever we have group 1 and group 2 metal hydroxides, oxides, or hydrides, you have a strong base. For example, let's take an alkali metal. Let's take sodium, sodium hydroxide, sodium hydride, sodium oxide, Na2O, that would be. Okay, these would be examples of strong bases where we have sodium as the cation. You can also have alkaline earth metals. So for example, barium. Barium is Ba2 plus. So barium hydroxide would have BaOH2 as its formula. Barium hydride would be BaH2 as its formula. And barium oxide would be just BaO to give a neutral compound. So when you put any of these in water, they're going to completely dissociate. Now, in this class, we're going to deal with the hydroxide strong bases. You won't see the hydrides and the oxides so much, although we will talk about them more in organic chemistry. So looking at the hydroxides of sodium and barium, it's important to note their stoichiometry. If I put sodium hydroxide in water, it breaks apart into sodium and hydroxide ions like this. So this would be my balanced dissociation reaction for sodium hydroxide. This goes 100% in the forward direction. This means that there's 1 mole of hydroxide that comes out for every 1 mole of sodium hydroxide that dissociates. By contrast, barium hydroxide has a different stoichiometric ratio. It also completely dissociates in water, but for every 1 mole of the barium hydroxide, I'm going to get 2 moles of hydroxide that come out because of the formula of barium hydroxide, the formula of that alkaline earth metal hydroxide. So we have to bear this stoichiometry in mind when we do calculations for strong bases. For example, let's calculate the pH of a 0.0050 molar solution of barium hydroxide. You really need to think about the stoichiometric ratio. So you have to write down the dissociation reaction, because that will help you to see that for every mole of barium hydroxide, you have 2 moles of hydroxide coming out into the solution. So that means that this solution, which has a 0.0050 molarity, this is moles of barium hydroxide per liter, right? That's the molarity. Looking at the reaction, I can see that I have 2 moles of hydroxide for every 1 mole of barium hydroxide. That's very important because I need to figure out the pH, and for the pH, I need the pOH, and for the pOH, I need the molarity of OH minus. So I have 0.010 moles of hydroxide per liter. So this is very important because it leads me to the pH. The hydroxide is 0.010 molar. And from there, I can get the pOH by taking the negative log. Okay, so the negative log of 0.010 is going to be 2. And the pH, I can get the pH from the pOH by subtracting from 14. So 14 minus 2 is 12. So the pH of my barium hydroxide solution is 12. Okay, so it's crucial to look at the stoichiometry of your strong base when you're doing a concentration calculation. This is a very high pH, which makes sense because it's a strong base. So we expect a very basic solution.